Now let's continue with our radiation. Now we had already calculated what I is. Let me just pick up the current. This is I of t. So if you just put it, here we have the mu 0 over 4 pi. So the vector potential just becomes mu 0 over 4 pi minus omega q0 sine of omega t minus omega r minus r prime over c divided by r minus r prime times dz. Well, you see, keep in mind, we are at a very far away point. So r prime is just along the z-axis. It has some magnitude between minus delta over, it has a magnitude smaller than delta over 2. Well, as r changes, r minus r prime change, as r prime changes within that range, r minus r prime doesn't really change much. The change in r minus r prime will be very small. And the changes will be proportional to delta over r. And keep in mind, we are at a very far away point. So if I just replace this whole expression by mu 0 over 4 pi times minus omega q0 sine omega t minus omega r over c divided by r I didn't really make too much of a difference. I already know that within that range, the integrand doesn't really change much. It is almost a constant within that interval. If I take it to be a constant whose value is given by its value at the center, this is what I would obtain. And keep this integral over here is delta. And that, keep in mind, delta is a small length. So any corrections to this expression are of the order of delta squared, which is small. And I'm just ignoring those things. I'm only keeping corrections that are proportional to delta. Any correction that is proportional to delta squared, I will just ignore. This is equal to mu 0 over 4 pi minus omega q0. This is AZ, yeah. Minus omega q0 times delta times sine omega t minus omega r over c times delta. But this is nothing but, again, mu 0 over 4 pi p dot, the z component of p dot, over r. Of course, p dot evaluated at t minus r over c. And the other components of A are 0. Because the current is running in the z direction, so the x component of the current is 0, and hence the x component of A is 0. The y component of the current is 0, so the y component of A is 0. This is the only non-zero component of A. Now let's start with B. B is equal to the curl of A. And keep in mind, A only has the z component, so this is the curl of A of z in the z direction. This is equal to, well, in the minus y hat direction, del over del x of AZ. And in the x direction, del over del y of AZ. Do you agree? Well, AZ depends only on R. It doesn't depend separately on X and Y. It depends on X and Y only through R. So I can use the chain rule. This is equal to minus Y hat, the derivative of AZ with respect to R, times the derivative of R with respect to X is X over R, plus in the X direction, derivative of AZ with respect to R, derivative of R with respect to Y is Y over R. So this is derivative of AZ with respect to R times 1 over R times Y in the X hat direction minus X in the Y hat direction. What is R hat, R cross Z hat? Let's see, this is X in the X hat plus Y in the Y hat plus Z in the Z hat cross Z hat. Is X in the X hat cross Z hat is minus Y hat. Plus Y hat cross Z hat is Y hat cross Z hat is X hat. Z hat cross Z hat is 0. So now we can write B in this form. Derivative of AZ with respect to R of 1 over R, R cross Z hat. Or derivative of AZ with respect to R, R hat cross Z hat. What is R hat cross Z hat?
Theta. Phi. Yok. Minus phi.
Let's say this is my R, this is Z. So R hat cross Z hat is somewhere in this direction. This is X, Y, and Z. This is derivative of AZ with respect to R minus phi hat. What is the magnitude? This angle here is theta, this angle here is theta. Phi hat has a unit magnitude, but R hat cross Z hat doesn't have a unit magnitude. So it has the magnitude sine of theta. So this is RB. First of all, what is the magnitude of R hat cross Z hat? Let's start with that one. No, magnitude. Is the magnitude of R hat is 1, magnitude of Z hat is 1, the sine of the angle between the two. So this is my R, this is my Z. This is my R, this is my Z. The angle that R vector makes with the Z axis is what we call the theta angle. No, I mean, you see, I'm not really going from one coordinate system to another coordinate system. What is this vector? I don't care which coordinate system I'm using. That is this vector, unit vector over there, this unit vector. R vector is the position vector. It is this vector. So if I take the cross product will have the magnitude sine theta. So that is one thing. Now, how I define the phi hat vector? Phi hat vector, I define it as, let's just take this point and rotate that point around the z-axis such that the angle that it makes with the x-axis is increasing. So that direction is the phi hat direction. So the direction of r cross z hat is the phi hat direction. Now let's take that derivative of az with respect to r. Here is my az. So B, in the radiation zone that is far away, I will be ignoring all terms that are proportional to 1 over r squared. This is equal to, well, if I take the derivative of Az with respect to r, I get this 1 over r squared term, which I'm saying that I'm ignoring in the radiation zone, that is the far away zone. So the only r-dependent term is over here. So I will end up having mu0 over 4 pi pz double dot t minus r over c times minus 1 over c over r times minus phi hat times sine theta. This is mu0 over 4 pi c. Let me just write pz double dot. In the phi hat direction times sine theta over r. Well, there are a couple of things. Plus, of course, there are terms of the order of 1 over r squared. First of all, there is a magnetic field that decreases as the inverse distance from the source instead of the inverse distance squared. So there is such a term. But this term is proportional to the second time derivative of the electric dipole. But you see, the second time derivative of the electric dipole, basically, it kind of means that the charges are somewhat accelerating. They should be accelerating. So it's the accelerating charges that is creating this radiation field, not the charges moving at constant velocities. Well, the derivation of the electric field in the radiation zone is also similar. I will not go over them. It's just taking the derivatives, taking the position and time derivatives, etc. The electric field in this radiation zone is equal to minus mu0, now plus mu0 over 4 pi pz double dot again, sine theta over r. This is in the theta this is in the theta hat direction. You see, you again see the same behavior. You get the second time derivative. It depends on sine of the theta angle, sine theta over r. It's perpendicular to that one. This is the radiating electric field. You see, it's the second time derivative. Well, in this problem, of course, these plus q and minus q charges are at rest. So that is the starting. We started from that one, and then we had this wire connecting them through a current. You could make the same derivation by taking these two charges, not connected, but just oscillating back and forth. You will basically get exactly the same result. In fact, once we also study magnetic dipole moment on this week, we will study it in general. We will see that whatever the charge distribution is doing, you can assign it some electric dipole, some magnetic dipole, and the radiation of the electric dipole will be always proportional to the second time derivative of the electric dipole moment. And the magnetic dipole radiation will be proportional to the second time derivative of the magnetic dipole moment. Now, what I would like to calculate is, we always said that, okay, so the radiation is, if my claim is that these are radiation fields, so these fields can go up to infinity. So let's calculate the Poynting vector. Well, it is mu 0, 1 over 4 pi squared, yeah, and sine theta over r squared, pz double dot squared, and we also have a factor 1 over c, and theta hat cross phi hat will be just r hat. So as we expect, it is going away from my source. My source is at the origin. So the energy is flowing away from my source. It goes as 1 over r squared. So if I integrate it over a surface at infinity, it will be a constant. It won't go to 0 as I take my surface to infinity. And yeah, those are the critical things. Let us calculate the total power radiated. Average over some time, average over one period, let's say. Now this will be, let me just write this, by the definition is the average S dot dA, which is mu 0 P0 squared omega to the 4 divided by 12 pi C. So this is the average power radiated by this charge.
P0 hocam.
It's the dipole moment.
T eşittir 0 mı?
Now, after all these derivations, derivatives, integrations, etc., this is why the sky is blue. This is why the sky is blue, the sunset and the sunrise is red.
Dalga boyu nasıl değişiyor?
Hmm?
Buradan dalga boyunun değiştiği nasıl?
Look at this dependence. The power radiated is proportional to the frequency to the power 4. So if the dipole moment oscillates very fast, the faster the dipole moment oscillates, the more power it will dissipate. Now let's imagine, why do we see a color in the sky anyway? You see, the atmosphere doesn't emit light on its own. So where does that color come from? Yes?
You were going to say something.
Huh? Yes, go ahead. I would rather if you say it.
The color of the oxygen molecules in ozone layer amplifies the wavelength of blue color of the sunlight. So when sunlight passes through the ozone layer, blue color, the wavelength of blue color gets amplified, and that's why we don't see other colors and we see just blue.
Well, let's see. I'm looking in that direction. Okay, today we have a nice day, the sky is blue, and I don't see the sun over there. So it's not the sunlight that is coming through towards me. So it doesn't make that.
The reflection.
The reflection. Well, the sunlight is reflected. The sun is, where is the sun? The sun seems to be somewhere over there. You see the sun is over there. I see this blue sky in that direction. So the sunlight from there, just as it's passing through the atmosphere, some of that light is reflected towards me or refracted towards me, whichever one you prefer. How does that work? How does I mean, we had all seen these reflection, refraction, etc., but how does it work to start with? I mean, you see, in real life, you cannot really change the direction of light. It's only gravity that changes the direction of light. The charges do not attract light, so the charges cannot really change the direction of light. But what they do is they absorb energy from light and emit it in a different direction. Just imagine yourself, here is the oxygen, nitrogen, or whatever molecule you have. Sunlight comes towards you. Well, you are made up of charges, right? So let's say you have a polarized light in this direction, let's say. And by the way, let me see, I erased it. This is why the light from the sky is polarized. And this is why this omega to the 4 is why the sky is blue. This is why the light from the sky will be polarized. So there are two things that is right on the screen now. So let's look at this atom. You send some polarized light in this, some of the light. So let's just pick up one component of the light coming from the sun. It hits their atom. So if it's polarized in this direction, the electric field at the position of the atom is oscillating up and down. So it will cause these charges to be oscillating up and down. Well, you see, this is a transfer of energy from electromagnetic radiation to the charges in the atom. So the intensity of the incident light will be diminished because some of the energy is transferred to the charges. Now you see these oscillating charges. They're oscillating, so they will be radiating energy, just like in this case. But you see, they will be radiating more energy the larger the frequency. And they are basically radiating in every direction, except then along their axis. You see, this sine theta behavior tells me that if the charges are oscillating in this direction, they are not radiating in the plus z, or they are not radiating in the minus z direction, but they will be radiating in the perpendicular to the z direction. So you see, sunlight is coming, it hits these charges over here, it causes them to oscillate up and down, and so due to these oscillations, the energy in the incident sunlight is just scattered in the perpendicular direction. Now, when I look at over there, I see the scattered light. But you see, higher frequencies are scattered more than the lower frequencies. Blue has a higher frequency than red. So when I look at there, not in the direction where the sun is, but in some other direction, the light that I see will be the scattered one, and the most scattered one is blue. So that's why when I look at the sky, it is blue. And sunrise, when I look at the sunrise, you see, during the sunrise, I look straight at the sun. What comes to me is the light that is not scattered. The blue frequencies, they have already scattered around. They will not be reaching me when I look at the sun straight. What will reach me is the red color. So that is what I will see. Do an experiment. How many of you are drinking milk? How many of you are drinking milk? Okay, good. So I'm sure all of you will be able to find some milk around. Take the milk, take a glass of water. In the water, put some milk. So you have these, the idea of the milk is it just creates a suspension made up of very small molecular pieces. And take some light, or just look through the glass, let's say. You will see that, for example, take some laser light, won't be so great, but some flashlight which ideally contains all the frequencies. Take some flashlight, shine it. If you just look at, if this is the glass, this is the light that you shine through the milk, you will see that it becomes red. You see the red color dominantly because the blue has already scattered around. Take your glass, shine the light like this, you will see that this milky water takes somewhat a bluish color. because you will see the scattered light. Now, the other reason why the light from the sky is, now the other thing, why is this color, the light from the sky is polarized? You see, the radiated light is radiated in the perpendicular direction to the oscillation direction of the charges due to this sine theta behavior. Let's just imagine this one. I'm looking at the sky in that direction. So I'm looking at in this direction. So the light should be scattered in this direction. Well, if the charges are oscillating in this direction, I will see light scattered in this towards me. So the component of the light from the sun that is polarized in this direction will be scattered towards me. That basically tells me that there is only dominantly one component of the polarization is picked up and sent towards me. So that's why I see a single polarization. It's plane polarized, not circular polarized, plane polarized.
But the transmitted radiation is polarized.
Well, you see, whatever light you have, you can write it as a sum of two perpendicular polarizations. One polarization is sent towards me, the other one continues forward. Both of them are polarized. Well, the polarization is, of course, not 100%, but more the component of polarized light in one direction, the component of light polarized in one direction will be more significant, more dominant than the other polarization.
So first, the radiation is coming from the sun, transmitted from the atmosphere, is polarized. Then the transmitted radiation is reflected.
No, not the transmitted one. You see, the ray is coming in this direction. Okay, this is the sunlight. I'm looking in that direction. Now, this light I can write as one component that is polarized like this, the other component polarized like this. Now, this component just is refracted, let's say, is scattered in my direction. This component is not scattered in my direction. So whatever I see in my direction is a wave from this polarization only. Let's see, what is the polarization of this radiated light? What is the polarization of the radiated light? You see, the polarization of light is defined as the polarization of the electric field. Electric field is in the theta hat direction. Theta hat direction, let's say if this is the z direction, the electric field that is coming in that direction will be oscillating like this. So that is the polarization. So if you are straight in on the xy plane, theta hat is basically z hat. It's in the same direction as your dipole moment on the xy plane only. So the scattered light, let's say, when I look at the sky, this is my observation angle, the light comes. So when this is the oscillation, this is the polarization of the initial light that will be scattered towards me, and the light that reaches towards me will be polarized in this direction. Well, what is the direction of polarization of your polarized glasses? You see, you don't want the sky to look completely dark, do you? When you put in polarized glasses, what you want is you just want to reduce the number of light entering your eyes. So I would rather pick circular polarizing filters for my polarized glasses. So that since the light from the sky is perpendicular, is plane polarized, circular polarized filters will only allow half of it to pass, and the other half will not pass. So I will reduce the light intensity reaching my eye by 50%.
Foton sayısını azaltıyor.
Yeah. That is Brewster angle that we had studied. The reflection is reduced if you are especially looking at a particular angle. And okay, if you are interested in photography, in photography you have these polarized filters, polarizing filters. So you can adjust its orientation so the sky becomes dark. So you can actually make the sky dark. Of course, the polarization, I mean, when I'm saying that the light from the sky is polarized, I'm not saying 100% polarized. Let's say, just if you make up numbers, 80% will have this polarization, 20% will have the other polarization. So it doesn't become completely dark, but it becomes quite dark. In particular? For example, glass. It does. I mean, you see, we had studied only one kind of polarization being reflected, but if you had done the homework or the exercise in your book, you will see that different polarizations are reflected by different amounts. The reflection coefficient for different polarizations are different. So even if you send a completely unpolarized light, which means it's 50% polarized in this direction, 50% polarized in the perpendicular direction, the reflected light will not be unpolarized. Basically, the same principle applies. Reflection is always absorption and then emission. Or in a different way, if you send light, it will just cause the charges to oscillate, and those oscillating charges are radiating. So that is what you see as reflection.
So that is why when, for example, we are taking a photo from a lake, and when we use filter, the reflection of the sky on the water will not be appearing.
Well, if you adjust your angle so that you are more or less at the Brewster angle, the reflection of the sky will not be visible.
Yani sadece o polarizm işe yaramıyor. Neydi o?
Polarizing filter. You have to be looking at the Brewster angle, which is somewhere around 40-45 degrees. For glass, for water.
Hocam güneşten çıkan ışınlar peki polarize mi?
No, they are unpolarized.
Ama hani plazmanın içinde de atomlar var ya, onlardan reflection olarak çıkmıyor.
Well, you see, the light takes around 10,000 years to, I mean, the light is produced at the center most of the time, most of it. I think it takes 10,000 years, if not 10 million, to reach the surface.
Güneşin içinde.
Yeah. It is scattered many times in random directions.
So, for example, for taking that, if even we don't use that polarized filter, and if we are in Brewster angle, can we do that?
No.
We can omit that.
No.
So both of them are required.
Both the filter and the angle are required.
Böyle gözünüzü kısın.
Try it. That's an experiment that you can easily do. Don't ask it, try it. Don't be lazy. Other questions?
In the beginning of the lecture, we said while limit r goes to 0,
R goes to infinity.
while calculating s dot dx,
While calculating what?
s dot dx energy flow.
In the beginning, you mean here? Oh, sorry. That is infinity. R goes to 0 doesn't really make, that is called the, R goes to 0 is called the near zone. So we basically have 3 different zones when you are studying moving charges. You have close to the charges, that is the near zone. You have far away from the charges, that is the radiation zone. And you have the intermediate zone. Any questions? Well, you see, for this calculation, we don't really care about that. What we are looking at is, I have some localized charge over here. Does the energy radiated, claimed to be radiated from this charge, does it go to infinity? Well, you see, if you have a closed surface at infinity, whether you take a sphere or a cube or no matter which shape, it shouldn't make any difference. You see, basically, you will try to label, let's say, the deviation from the average radius, and that will eventually go to 0, whatever complicated shape you have for an infinite object, infinite surface. Well, let's see, P double dot is equal to minus omega squared P because of the particular choice of the dipole moment we have, or of the charges. Well, it doesn't really make too much of a difference because whatever motion you have, you can always write it as a sum of some cosines and sines of different frequencies. Now, that's basically what we are doing when we are discussing the the scattering of light from the atmosphere, because the sun sends many frequencies. So the motion of the charge will be quite complicated. Motion of the charges of the atoms. But I can still write them as sum of cosines and sines, and each will behave as if they are independent. And each frequency will radiate power at its own the power radiated at each frequency will be determined by the frequency of that component only.
Hocam, o zaman bu atomun içinde elektronlar var ya, hareket ediyorlar, birbirlerine yaklaşınca itecek ve ivmeleri değişecek. Işıma yapıyorlar mı o zaman?
Well, that, according to classical electrodynamics, they should radiate. But somehow they don't. So that was one of the puzzles before the advent of quantum mechanics. Now quantum mechanics tells us why not. Now, I will not go into the details of the magnetic dipole radiation, but let's just imagine a ring, and the current will be time dependent in this ring. Let's say this is my I, positive direction. And you can define a time-dependent magnetic dipole moment as, let's say, the radius is r, I of t pi r squared in the z direction. Now, in the remaining week, time in this week, we will be mainly studying some arbitrary charge distributions. But if you look at this, I mean, in this system, you don't have an electric dipole. You only have a magnetic dipole. In the previous case, although we had this current, since the current doesn't form any closed loops, the magnetic dipole was 0, the electric dipole was non-zero, and the radiation was hence called the electric dipole radiation. In this system, there is no charge accumulation anywhere. The charge density, the volume charge density is 0 everywhere. So there is no electric dipole over here, but there is a magnetic dipole. So this is the radiation emitted by this system is called the magnetic dipole radiation. And let me just write down the final answer for the magnetic dipole radiation. the electric field in this radiation zone is just mu 0 mu double dot, sorry, minus mu 0 mu double dot over 4 pi c sine theta over r in the phi hat direction. It just looks like the previous case, more or less. There is this sine theta over r dependence. Well, of course, in the previous case, the electric field was in the theta hat direction, the magnetic field was in the phi hat direction, so here we have kind of those two things are reversed. But the general behavior that it depends on the second time derivative, it depends on this factor, sine theta over r, is common, and B is similarly mu 0 over 4 pi c squared mu double dot sine theta over r in the theta hat. Basically, whatever we said in the previous case also holds over here. So if you have a magnetic dipole aligned in the z direction, you see the magnetic dipole is aligned in the z direction, you still get some radiation field if the second time derivative is non-zero. And just considering that this magnetic dipole moment, which is given by the currents, the velocity of the currents, this second time derivative of mu basically means the charges should be accelerating. If the charges are accelerating, you get the radiation. And again, the E cross P, the pointing vector will be in the z direction, in the radial direction, so energy will be dissipated. And more or less, you get exactly the same picture.
John, what is mu?
Mu is the magnetic dipole moment, mu of t. So this is mu of t. Magnitude of mu.
Buradan şey söyleyebilir miyiz yani?
Or let me put it in this way, sorry, not the magnitude. Mu vector is mu of t in the z direction.
Buradaki şu iki denklemi birleştirince şey diyebilir miyiz acaba? Bu manyetik dipol eşittir işte C çarpı elektrik dipol.
No. No, in general, no. They look mathematically the same. That doesn't mean they are related. Okay, so I will just end the lecture here today. And on Wednesday, we have 1 hour of lecture, followed by recitation, where we will be discussing, if you want, the midterm questions. I will try to prepare the solutions today or tomorrow, so you will have a chance to look at the solutions before coming to the lecture. And on Friday, we will have 1 hour lecture, 1 hour recitation. At 8:40, we will have a lecture. No, we will be basically dealing with, okay, here we just picked up two specific examples of an electric dipole and a magnetic dipole radiation. Now, in general, we don't have these systems. What we have is we just have a localized charge density located within some volume, and they will be doing some kind of an arbitrary motion, let's say. Will they radiate? How much will they radiate, etc.? And another question for you. Let's just take 1 point charge, attach it to a spring. Let us just make it to the accelerated motion. Well, since it's let's just pick up a harmonic oscillator, put some charge on your oscillator. It will be an accelerating charge. So it will radiate energy. It will lose energy. So it will slow down. Its amplitude will change in time. Well, you can basically model it as a kind of a force acting on my charge. So what is that force?
The attraction of other charges.
There are no other charges. You have a harmonic oscillator that's just a charged harmonic oscillator.
Friction.
There's no friction. But of course, the effect of this electromagnetic back reaction is similar to friction because eventually the oscillator will stop. It will just radiate away all its kinetic energy in the form of electromagnetic radiation.
Gravitation.
There's no gravity in the problem, just electromagnetic field forces.
Going to the supreme potential energy?
Sorry?
Going to the supreme potential energy.
Eventually it stops at the equilibrium point. You see, it goes to infinity because of electromagnetic radiation. Just to think over it. Okay, see you on Wednesday.
The moving charge may create some current, but very, very limited current. Just in that.
Okay, so?
It may create a magnetic field due to its motion, so the magnetic field will apply some forces on the charge.
And you see, energy should be conserved. So basically, of course, it's the fields that are kind of creating a force, but it's going to infinity. So what is this force? I mean, I'm not asking you to describe it, quantify it, calculate it.